This is our pre-lab discussion on a lab called Identification of a Compound by Mass Relationships. We are going to be given an unknown solid salt, and based on mass percentages, we are going to work to identify the unknown through a process of heating and using acid. Our pre-lab discussion is found on page 13 in your lab book. On this page is giving us the identity of 4 possible salts, which one of them we will be given. The first says sodium hydrogen carbonate, NaHCO3. Sodium hydrogen carbonate is sometimes called sodium bicarbonate. It is actually baking soda. The second sodium compound we're given a choice of is sodium carbonate, Na2CO3. Notice the difference in structure here, a hydrogen carbonate or bicarbonate versus strictly carbonate. Carbonate is a polyatomic, carries a -2, so of course we would see that sodium with its +1, when we crisscross we get Na2CO3. Now the bicarbonate polyatomic is a -1, and so therefore when we hook it to sodium we see the 1-to-1 subscript ratio. So 2 possible sodium salts, or perhaps you'll be given a potassium salt, such as potassium bicarbonate or potassium hydrogen carbonate, or again, it's potassium carbonate with no hydrogen involved. So one of those 4 possible samples, and they're going to be in jars labeled unknown 1, 2, 3, and 4, and you'll be given one of these to identify. Well, the first part of our experiment is going to be, let's determine if we have a bicarbonate or strictly carbonate, and we can do that by a simple heating process. So the first part of the experiment is designed to conclude, do I have this side or do I have this side? Do I have a bicarbonate or do I have a carbonate? And really what we're going to do by heating, if we have a bicarbonate, we're going to drive out water and carbon dioxide. So this side, if indeed we have a bicarbonate, loses an appreciable amount of mass when heated. Whereas on the opposite side here, the mass remains constant. There is no water and carbon dioxide to drive out. It's a dried salt. So one of the first things we'll do is to determine, am I a bicarbonate or a carbonate? And so the directions will tell you to weigh out a known mass of the unknown. And the unknown mass you're going to record into your data table. You're going to heat this substance over your Bunsen burner, and the heating pot is called a crucible, and you'll use a clay triangle sitting on a ring stand, and then you'll place your pot there. So just kind of a visual, this would be your ring stand, this is your burner, a clay triangle sitting over your ring here, so this is on your ring stand, and a clay triangle really is just literally that, 1, 2, 3, best I can place a triangle there, and then your cooking pot will go inside the clay triangle with a lid on it, and this of course is where your sample is in the bottom of this cooking pot here, known as a crucible. These are in your stock drawers, alrighty? And you're told to heat that, and really there's nothing to observe other than just a little bit of patience, other than weigh it before and weigh it after. If you notice that it has an appreciable mass change, you've determined it to be a bicarbonate, and if you determined that the mass stayed relatively constant, you now have determined you have a carbonate. We don't know the first name, could be sodium or potassium, but at least we know what the last name is. So if indeed, and let's just kind of think this through, if we have a bicarbonate, and again the first name could be sodium or potassium, we have no idea at this point, and we heat it, it will decompose to give us a sodium carbonate, and out of the dish came carbon dioxide gas and water gas or steam vapor. So here, just to keep this balanced, we'll need a 2 out here. So just thinking about the law of conservation of mass, I'll just make up a number. If I started with 3 grams of this baking soda, NaHCO3, I heated it to force a decomposition to be left with a carbonate, I would expect a mass loss. CO2 and water both left the dish as gases, and of course, just making this up, you'd have about 1 gram loss, but definitely a noticeable difference between the starting and ending mass. However, if, and I don't know, but if I started with a carbonate, and you could see carbonate upon heating would still form carbonate, and the mass would remain constant. So step 1 of your procedure, we're going to determine, do I have a bicarb or carbonate? Regardless of what you started with, everyone at the end of that first heating process now has some sort of carbonate in the dish. Either you started with it if it remained constant, or you produced it if you lost mass. So step 1, making sure we all are proceeding to step 2 with a carbonate. Alrighty, you might have had to decompose, or you had it originally. Now again, this could be potassium, it could be sodium. I'm just going to keep with sodium just to keep the example going of the procedure. This is sitting now in my crucible, and I'm going to let it cool. I'm going to let it cool so that when I go to the next step, taking this carbonate, Na2CO3, and adding acid, I do not want to drop in concentrated hydrochloric acid into a hot crucible filled with a hot salt so that it starts to bubble up on me. Be very careful and let it cool before you move to this next step. So once your dish is cooled, your directions will say add between 25 to 30 drops of HCl slowly into the dish. And the reason I'm saying slowly is because we're going to start producing bubbles, and the bubbles themselves, we don't want it to overfizz. Now think about the pattern of change. Double displacement. Na goes to Cl, H goes to CO3, and think about charges. And so if I go Na is a plus, Cl is a minus, sodium chloride, and and H goes to CO3, H is a plus, CO3 is a minus 2, so we get H2CO3. Alrighty. But now what do you remember from our last series of lessons in chemical reactions? That this carbonic acid, that's the name of the acid formed here, as soon as it's forming from a double displacement, you will see definite evidence of a chemical change as it begins to decompose. It's so relatively unstable that it decomposes and gives off the driving force of carbon dioxide bubbles. This is the driving force of this double displacement reaction, the bubbles of CO2. So this is made but decomposed immediately into liquid water and carbon dioxide gas. So we have salt water left in the dish because carbon dioxide bubbled out. So let's think about that. We have salt dissolved in the water, and we had sodium carbonate. It started as a salt. We put in aqueous hydrochloric acid, so solid dropped into this acid. It bubbles left the dish, and now we're left with salt water. What we want to find out, this is our desired mass right here. We want to know the mass of the dried sodium chloride. So the directions will say simply, put it over a flame and gently heat it. So that's exactly what I'm going to go do. Now I have salt water sitting in my crucible. I'm going to put it back over the flame, and I'm going to dry it gently. Please do not overheat because it will spit and spatter and all your salt will land on the tabletop. Slow heat with a lid that's kind of half on, half off, and because we want the steam to be able to evaporate out. We don't want the lid to prevent the evaporation process, but a little lid doesn't hurt to help prevent any kind of spitting and spattering. You got to keep an eye on it, and then of course adjust the flame immediately if it starts to spit and spatter. We don't want sample lost. We want to know the mass of the dried salt. Alrighty, so I have to cook it again. So HCl, about 25-30 drops, no correct amount, just go slow to prevent over fizzing. Once the fizzing has stopped with the addition of the acid, place it back over the burner and dry it up. When I'm dried, I have residue of salt. Now remember, this might be potassium or it might be sodium chloride. But that dried residue is what we want the mass of. Alrighty, so initially, I know the mass of my initial reactant. I know the mass after the first set of heating. It may or may not change. The next recording is the mass at the final end, and it's now a chloride salt. Might be potassium, might be sodium chloride. And those really are the measurements that we need to go on and actually form a conclusion of what the unknown was. We're going to do that by a concept called mass percentage. Alrighty. So let's first of all talk about a theoretical percentage by mass. And let's just take, maybe we'll start with that NaHCO3, the sodium bicarbonate salt. And this would be unknown 1, 2, 3, or 4. It could be any of those 4. But it definitely will undergo a decomposition followed by a double replacement. And at the end, you'd have sodium chloride. After the addition of acid, you produce sodium chloride. Alrighty. And so if I think about the overall reaction, we all started with a sodium or potassium carbonate, and then went on to produce water and carbon dioxide. Starting with the sodium carbonate, we went on to produce, so for this particular reaction, we went on to add the acid, and out came sodium chloride, carbon dioxide, and water. We got rid of these, and this is the mass. Alrighty. What we'd like to know is the mass percent of the sodium salt we produced compared to the original mass of the salt. And let's take some practice data, and that would be a good place to start here. Just so we have some common numbers, we'll go to the advanced study assignment next. So now let's go ahead and flip a page over, and this is on page 17. We talked about a little bit of the procedure and the overall purpose to determine the identity of our unknown based on mass relationships, percent composition, part over whole to give a percent. In reading through this pre-lab data, it says, a student attempts to identify an unknown compound by the method used described in this experiment. She finds that when she heats a sample weighing 0.5015 grams, the mass went down appreciably to 0.3432 grams. Then at the very last step, after the addition of the acid, the converted chloride went to 0.3726 grams. So I just created a spot, and this is not in your page 17, but it helped me just to kind of clarify what those three numbers were. So the very original mass, 0.5015, I put it over a flame, and look, it lost weight. After I added HCl acid and dried it up again, the chloride salt that remained is 0.3726. Let's go through using these numbers to decide what is the identity of my unknown. If this indeed were my lab experiment, the three collected data points, what was the identity of the unknown? So first off, is the sample a carbonate? Give your reasoning. Remember the previous page? If the sample were a carbonate, the mass would have remained constant. If the mass went down an appreciable amount, we knew it to be a bicarbonate, that there was a hydrogen involved, and we dried it by heating it. So was this indeed a carbonate? We can clearly see no, it must have been a bicarbonate because the mass changed. Due to the mass change upon heating, the sample must have been a bicarbonate or hydrogen carbonate, whatever you prefer, but it's not strictly a carbonate, it's a bicarbonate. So HCO3 negative is now the last name. So I know with confidence, because it lost weight upon the first heating, it's a bicarbonate polyatomic ion. Just to clarify, if I start and end in this very first heating process and the mass does not appreciably change, we knew it to be a carbonate. Since it did change, it must have been a bicarbonate. And so now the part B says, well, what are your two choices right now? If we know the last name is bicarbonate, choice number 1 could have a sodium as the first name, or it could have had a potassium as the first name. But we know with confidence it is not sodium carbonate or potassium carbonate, that it has the hydrogen as part of its original formula due to the mass loss upon heating. Write the chemical equation for the overall reaction that would occur when the original compound was converted to a chloride. Our compound is indeed a hydrogen carbonate, so we have to use 2 equations. If in your lab you determined to start with a carbonate, you would only have 1 equation. We're going to write this for the sodium salt and then for the potassium salt. So the sodium salt first. If indeed we started with sodium hydrogen carbonate and we heated it, it would force the decomposition to produce the carbonate salt, releasing water and carbon dioxide. 2 NAs, 2 Cs, and so forth. We balance that equation here. Then this reactant, this product becomes the reactant of the next step. We're now starting with Na2CO3, and we add the addition of the acid, about 25 to 30 drops, slowly to a cooled sample. And we realize that we got NaCl and water and carbon dioxide upon the decomposition of the carbonic acid. H2CO3 broke down. Alrighty. We need to balance 2 NAs, 2 NAs, and we'll need 2 H's and 2 Cl's. A 1, 2, 2, 1, 1 balances that equation. So here's the first equation. Then it's to do the same thing but for the potassium. And so just to follow directions, I'll change color here. We're going to do the same thing. Should go faster. We have potassium hydrogen carbonate being broken down into potassium carbonate, water, and CO2. This dried salt of potassium carbonate, upon the addition of acid, oops, I'm sorry, let me erase. I have to add the acid. My bad. 25 to 30 drops to a cooled sample. Out comes potassium chloride and water and CO2. And we'll keep it balanced with a 2 and a 2. Alrighty, so 2 possible choices. We're now trying to determine with this setup data, is this the original reactant or is this the original reactant? And this is the chemistry involved. Now remember, in your real lab, if you started with a carbonate, you only have 1 equation to write when it comes time to doing your own processing. Letter D asks us to consider some stoichiometry. How many moles of chloride salt would be produced from 1 mole of the original compound? Let me change color here. I'm noticing that a coefficient of 2 is in front of the original reactant, and a coefficient of 2 is in front of the chloride salt. For every 2 moles of the initial reactant, we produce 2 moles of sodium chloride. Well, what if instead of 2, we only started with 1 mole? We could clearly see that we would produce 1 mole of sodium chloride. Since the stoichiometry is 2 makes 2, 1 would make 1. For every 1 mole of the original carbonate, of the original bicarbonate, of the original reactant, we can say, 1 mole of chloride salt would be produced. And really that's nothing more than a little stoichiometry. If I started with 3 moles, I'd produce 3 moles because they are indeed the same number. Whatever I start with, in mole value, not mass, but in mole, I'll produce the same amount. So how many grams of the chloride salt would be produced from 1 molar mass of the original compound? So 1 molar mass is, to me, kind of a funny way of saying 1 mole. If I had the molar mass of the original ingredient, that's the same as saying 1 mole of the original compound. And so previously we worked up a little bit of molar mass in our mole chapter, and we're really just adding the weights off the periodic table to find molar masses. And so for instance, off the periodic table, sodium weighs 23, hydrogen is 1, carbon is 12, and oxygen is 16, but there's 3 of them, so I'm going to simply add, and I have my calculator here. I go 23 plus 1 on the hydrogen, plus 12 for the carbon, plus 16 times 3 for those 3 oxygens, and the molar mass of NaHCO3 I sum and found 84. Let's do sodium carbonate. So sodium is 23, but there's 2 of them, so times 2, plus 12 for the carbon, plus 16 times 3 on the oxygen, and this has a molar mass of 106. 2 NAs added to a C added to 3 O's, 106. How about sodium chloride, NaCl? With NaCl, let's see, 23 for sodium, and I'm going to use 35.5 for chlorine. So 23 plus 35.5, and you found, like me, I'm sure, 58.5 grams of salt. Same work here. Let's find molar mass. Potassium, I call that 39. 1 for the hydrogen, 12 for the carbon, and 16 times 3 for the oxygen. So let's sum that together. Work it with me. You realize I'm not perfect on the calculator. 39 plus 1 plus 12 plus 16 times 3. This has a molar mass of 100. How about potassium carbonate? 39 times 2 plus 12 plus 16 times 3. That's the mass of 2 potassiums plus 1 carbon plus 3 oxygens, and this I'm finding to be 101. Which makes me wonder. $39. Just checking my math. I am really good at just double checking, make sure I don't have a mistake. 100, 39 plus 1 plus 12 plus 48. Yeah, all right, I got 100 several times here. Let me try this again. 39 times 2 plus 12 plus 48. And I got 138. There's the error. I knew that I couldn't have had those two come out so darn close, so I knew I made a mistake. 39 times 2 plus 12 plus 48. I'm sorry, I'm pausing because I'm checking my math. 39 times 2 plus 12 plus 48. I get 138. All right, thank you for your patience there. I just wanted to be sure I didn't carry a mistake forward. 39 plus 35.5, and this guy has 74.5. That looks better. I knew I messed up here because those came out too similar. Alrighty. So for instance, if I have 1 mole of a sodium salt, and by the way, right off the bat, based on this data, I have to decide, am I going to start with this or this? Because we determined, due to mass loss from the original reactant, we don't have a carbonate. Now in your real lab, you might need to start here. And if you consider that, for every 1 mole of the carbonate, you produce 2 moles of the salt. So I just want to emphasize a real important point. If your unknown was indeed a carbonate, you have a 1 to 2 stoichiometric ratio. For every 1 mole of the original reactant, you produce 2 moles of the chloride salt. If you're starting like this particular example with a bicarbonate, you have a direct relationship. For every 2 makes 2, 1 would make 1. But if you're starting with a carbonate directly, a 1 to 2 ratio, you'd have a 1 to 2 ratio. So here I would have 1 mole making 2 moles. But here, if we're using bicarbonate, we have a 2-to-2 ratio. Very important to remember your stoichiometry, and it just so depends upon what your unknown did in that first heating. Since ours lost mass, we know that we had a bicarbonate. But if it didn't lose mass, consider the stoichiometry critical right here. If we started with a sodium salt, 84 grams would have produced 58.5 grams of chloride salt, a direct relationship. If I had 100 grams of the original reactant, I'd have 74.5 grams of the potassium chloride salt, a direct molar ratio. But remember, if you are looking at this ratio, if your lab is giving you a carbonate to start with, let's just suppose, and it's just so made up right now, if your lab started with a carbonate and I had 106 grams of Na2CO3, 2 moles of sodium chloride form for every 1 mole of Na2CO3, then 58.5 grams of your NaCl per mole would form. See how you'd have twice the value as our answer here. So important that the heart of your stoichiometry problem is considered. A direct ratio for a bicarbonate, a 2-to-1 ratio for a carbonate. If you had 100 grams, whoops, this is not part of pre-lab, but it's allowing me to prep up in case you get a carbonate. If you had 1 mole, which was 138 grams of your potassium carbonate, you'd have 2 moles of KCl form for every 1 mole of your potassium carbonate. So what we're saying here is if in your lab, your actual lab data, these values would be twice as much as what we just calculated here. Hope that clarifies. What is the theoretical mass ratio, mass of chloride to mass of the original compound? Alrighty. So the mass ratio, thinking about part over whole to find that. So the mass of the chloride, and shall we do sodium chloride just to kind of think about an example here? 58.5 grams was produced from the original salt of 84. And you could just express that as a percent and leave it as a percentage. We don't have to work it to a whole number. Or if you had a KCl, its original value, 74.5 over the original 100. Express that as a percent. So this is your KCl. This is your original mass of the sodium salt, which for us we knew to be KHCO3 for this example. This would have been NaCl over NaHCO3. And these are just molar masses. So theoretical, use molar mass. And so we can hit that, see what we find. 58.5 divided by 84. Let's express it as a percent. That's easier. That's what, 69.6%? 74.5 divided by 100 is the molar mass. Move your decimal for a percentage, and we literally get 74.5% by mass. A mass percentage. So using molar mass for theoretical ratio. The observed mass ratio, that goes back to the data table. So remember this little data table I had created way up here? This was the mass of the chloride, the final weighing. This was the mass of the original sample, the initial weighing. This is what we're going to compare. So 0.3726, let me scroll back down. Over the initial mass, 0.5015 grams of bicarbonate. Let's express that as a percent. So the final weighing over the initial weighing, 0.3726 divided by 0.5015 times 100. We get 74.3. So this is my experimental mass ratio. This is my theoretical. It's just time to take a look. This is the mass percentage of sodium. This is the mass percentage of potassium. Who are we closest to? Our calculated answer from the lab result, 74.3, is very close to the theoretical for the potassium compound. It is farther from the sodium. This is a very good result. This is the identity of my unknown. Your calculation has now verified the unknown in this particular experiment is the potassium hydrogen carbonate. By the time you're done calculating your initial and final weighing ratio, so your final compared to your initial, you're going to find a percentage, part over whole. It will either be bicarbonate if it lost mass, and now you're able to identify with confidence the identity of your unknown. So I look forward to seeing you in lab this week. I hope this video has helped prepare you